If k is equal to the floor of this expression, then we have that this cube root is between k and k plus 1. Let's take a look at the cube root of 1. This is going to be less than the cube root of 2, and so on. The cube root of 1 is 1, and the cube root of 8 is 2. All of these numbers to the left, all the way up to the cube root of 7, the floor of all of these expressions, these are all going to be equal to 1. The floor of the cube root of 8 is going to be equal to 2. That's also going to be true for the floors of the cube roots of 9 and the other consecutive integers up to, but not including, the next perfect cube. That goes up to the cube root of 26, because we have that the cube root of 27 is 3. So that's going to be the same as the floor of the cube root of 27. So let's take a look at the number of values of n for k equals 1. We get that when we take the cube roots of 1 through 7. We're looking for a k that gives us 70 of these solutions, where k divides n. Here, the number of solutions, since 1 divides everything in this list, is 7. And then for k equals 2, our solutions for cube roots go from 8 to 26, and we're only interested in the ones that are divisible by 2. To count these systematically, I'm going to replace this first element in the set with 2 times 4 up to 2 times 13. This is all of the even numbers between 8 and 26. So counting the number of solutions, we'll take 13 and subtract 3, and this is 10. Let's try one more example where k is equal to 3. Our possible cube roots start with 27. Our next perfect cube is 64, so we'll stop here at 63. Replacing this with the integers that are divisible by 3. Our first one here is 27, or 3 times 9. Our last one in this list is 63, or 3 times 21. So the number of elements that are divisible by 3, we'll take 21 and subtract 8, and we get 13. We're interested in achieving 70 solutions, and we're still far less than our goal. So we'll generalize. Again, we'll go back to our definition of the floor function. This means this expression is between 2 consecutive integers. We'll take this chain inequality and cube all 3 sides, and I'll expand this right-hand side. I'll replace this less than with less than or equal to by subtracting 1 from this expression to get the next integer below that. And as in our earlier examples, we have that k divides our first and last consecutive integers in our set. All the solutions here are going to be k cubed and the consecutive integers after that. And then this is our last element in the set. We want to replace this with all the numbers that are divisible by k, and we'll count these again in the way we did in our previous examples by pulling out a factor of k. And I'll do the same thing with this. And now I can count the number of solutions by taking this last factor and subtracting 1 less than k squared. So for any value k, the number of solutions, n, is 3k plus 4. Let's set this equal to 70 and solve for k. The problem asks to maximize the ratio ni over k. To do that, we'll maximize the numerator. Our maximum value of n sub I is this over here. So ni over k, we'll plug this in, divide by k, and plug in k equals 22. And our answer is 553. If you'd like me to solve any other math contest problems, please leave them in the comments.